Assalamualaikum, this is Anna Fatma. Welcome to my YouTube channel. In this video, we will discuss about Leibniz series. So I have already discussed this formula with you guys in my previous video. I would like you to watch that video so it will help you to understand this formula. Moving towards our question. So our question is y is equals to sine inverse x whole square. We have to prove two parts. The first part is 1 minus x squared by 2 minus x by 1 equals to 2. And then the second part is yn plus 2, which is the nth derivative of our function. I suggest you to pause the video here and try to solve this question. You need to prove this part. I think so it will be easy for you to solve this, because all you need to do is take 2 times derivative of your question. Okay, if you have proved this, then excellent. But if you don't, so don't need to be worried about this. I am here with the solution. So we will simply write our function, which is this. Now we will take the derivative of our function. The derivative of y will be y1 and the derivative of sine inverse x whole square. So what we do, we take the power, we write the power first. So here is 2, then write the function itself, the variable itself. So we have written the variable here, and now we will take the derivative of our function, our variable. So the derivative of sine inverse x is 1 upon under root 1 minus x square. That's it. Our first derivative is complete. Now I have simply multiplied this under root 1 minus x squared with y1 to simplify our function. Now what I did, I just simply squared the whole value, which is y1 squared 1 minus x squared equals to 4y. Why did I square the value? The question is this, because what I saw there, I saw that there is sine inverse x, and I saw in our function that the square of sine inverse x was y. So I got an idea to square the whole function. It will also cut this square root and will make my function simpler in terms of y, because I saw that our answer is in the terms of y. Moving to our next slide. So I just simply wrote that previous values, which was this, in the next slide for your convenience. Now I will differentiate it second time. So that now what I do, I simply use the formula of u dot v. So the formula is written here, which is u dot v equals to u derivative of v plus v derivative of u. So what is u here? U is y1 squared and v is 1 minus x squared. So u, we simply wrote the u derivative of v, which was this. This was u and this was v, right? So the derivative of v, the derivative of constant will be 0, so 0, and then minus power is written first like here, so it will be 2, and simply wrote the function, which is x. So power minus 1 will be 1, so it will not affect our variable. So I simply wrote minus 2x. Now plus sign from there, and for v, I simply wrote the v here, and u derivative of u. Our u was y1 squared, so the derivative of y1 squared will be 2y1 by 2. How? The power will be written first, so 2y, and we will take the derivative of our function, our variable y1. So the derivative of y1 will be y2. The second derivative of our y1 will be y2. Simply I wrote this y2 here, and then 4y1 from there. The 4 is coefficient here, so it will not be derivated, and we will derivate this y. So the derivative of y will be y1, so I just simply wrote it here. Now I just multiplied the whole values, took common there, and now we have proved 1 minus x squared by 2 minus x by 1 equals to 2. We have proved this part. Now for our second proof, I would like you to observe the pattern. So for nth derivative, the nth derivative of this part is n plus 2, which is the second derivative of our original function, which is this, and for this it is n plus 1, which is the first derivative of our original function with some nth value, right? I want to tell you is that if you are not asked to prove this, you still have to take 2 times derivative of your original function in order to prove this, because n plus 2 is making it obvious that you have to take 2 times derivative of your y and then apply Leibniz series over it. So now what I'll do, I'll take this part and apply Leibniz series over it, and then take this part and apply Leibniz series over it. So let's move. This is your equation number 3. After applying Leibniz series over this part and this part, whatever will be the result of both of these will be put in this equation, which is equation number 3. Now for 1 minus x squared y2. So here u will be y2 and v will be 1 minus x square. Why? I have told you the reason in my previous video. So that's why I would like you to go and watch this. So v is equals to 1 minus x square. I'll take its derivative. So v1 will be minus 2x and v2 will be minus 2. We always take v, the part, the value, the function which will be reduced itself into a constant value. So what we observe that we have to take 2 times derivative of our this part to get the constant value. So for u it will be y2. The first derivative u1 will be y2 plus 1 and the second derivative u2 will be the fourth derivative of your original function and the second derivative of your y2, right? So yn will be yn plus 2 because the Leibniz series is going to be applied on your original functions. Here that is why yn plus 2 is written. Un minus 1 will be yn plus 2 the whole by un, right? So un was yn plus 2, so that is written here, and minus 1, so it will be yn plus 1 and un minus 2 will be yn. Now this is the formula of Leibniz series. So uvn, which is 1 minus x square n, equals to un, which was yn plus 2, v was 1 minus x square plus n from there, and un minus 1 was yn plus 1, v1 was minus 2x plus n into n minus 1, un minus 2 was yn, and v2 was minus 2. And then I just simply wrote the value. This is your equation number 4, which will be put into equation number 3 soon, right? For x, y1. So u is y1 and v is x here, because we know that by taking its first derivative we will get the constant value, which is 1. So u1 will be y1 plus 2. To observe the pattern, that's why I have take 2 times derivative of u. So u2 will be y1 plus 2. Now listen to it very carefully. By taking the first derivative, which is u1, 1 is added into your function, which is y1. By taking the second derivative, which is u2, 2 is added into your original function, which was y1. What we observe that by taking first derivative, 1 was added. By taking second derivative, 2 was added. Similarly, by taking nth derivative, n will be added to your original function, which is y1. So un minus 1 will be yn plus 1. So un was yn plus 1. So un yn plus 1 and minus 1 is written here, which is equals to yn. And then I just simply put the formula of Leibniz series here, which is this. So xy1 equals to xy n plus 1 plus n yn. This is your equation number 5. Using equation 3, 4 and 5, what we will do, we will substitute these values to the equation number 3. The 4 and 5th equation will be substituted into equation number 3 because this is the nth part and this is also the nth part, right? So I just simply substitute the values here, which was 1 minus x square yn plus 2 minus 2x n y plus 1 minus n into n minus 1 yn. So this, the whole part, this whole chunk is equivalent to 1 minus x square y2's nth derivative, and then the minus is from there, and x y1. So this chunk is the equation number 5, which is this. In this step, I just simply multiplied the values using algebraic multiplication, and now cut the values for the third step, which was plus nyn and minus nyn and minus 2x nyn plus 1 minus xyn plus 1, right? That is simply written here. Now by taking common, we have proved the second part of our question. That's it. The end. I hope you like the video. Allah Hafiz.